Now, you know the Kandinsky, obviously. I'm talking about the Russian artist, Russian painter that redesigned the geometrical shapes in his artwork, and is compared to Picasso and Monet. And now Kandinsky was created together with by Sber and together with AIRI experts, and you can generate the artwork in 1 minute with text prompt. What is being changed in Kandinsky and how this artist skill can be delivered to you. This is going to be shared. This is going to be presented by Denis Dimitrov from Sber and AIRI. The topic is Kandinsky. Very simple and minimalistic. And the floor is yours. Thank you very much, Valentin. Hi all. I'm going to talk about our Kandinsky model, and well, I'm going to start with the content generation problem, talk about the diffusion models. We're having a scientific day, so let's look at the formulas. I'm going to talk about two models that we announced today, Kandinsky 3.0, thank you, and the new model for generating the images with text prompts, and Kandinsky video model, the first video generation model, the full-fledged video generation model. Well, let's start from the beginning.
Task history. The task of generating images or generating whatever is a very new one. In 2014, the first paper on GANs appeared, generative adversarial networks, and not even 10 years elapsed since then. But since then, the research on GANs has been developing very rapidly. In 2016, we got the first research paper on image generation from textual descriptions. So generation of images is an inherent part of it. The number of generative architectures and the principle of generating anything in engineering and in research has been widely used, including GANs. GAN consists of a generator and a discriminator, the adversarial parts, and their training had to be announced. It is a complex process which requires manual fine-tuning, which means it is a difficult endeavor to train GANs. So there was an attempt to train it with the projects that are in closer proximity in the latent space, but then there was a problem with the decoder, and you get something unintelligible as the output. Flow-based models, their disadvantage was that they needed some backwards function, which is once again complicated. But very recently we got diffusion models, which do not have all these shortcomings, but they do have one disadvantage, that the inference with the diffusion models takes a long time because it is a multi-step process. Speaking of Sber and AIRI, we have been doing this image generation task not for a very long time. We started in 2021, and since then we got 6 architectures, with Kandinsky 3.0 being the latest. We started with Malevich and Kandinsky 1.0. They were basically translators, transformers that were invented to translate from one language into another, from English into Russian, for example. So Malevich and Kandinsky were translating from the language of from the Russian language of text into the language of image. The image-based language is not just text, it is tokens. Tokens that appear through the use of Wakugan, this other neural network. The generation, the translation from text to image is challenging because text is not a 2D structure. And then with the emergence of diffusion models, the diffusion models have been way ahead of all the other models. Kandinsky 2.0 and 3.0 are obviously diffusion models. So what is diffusion? Diffusion is a multi-step process of diffusing an object. As you remember from chemistry lessons, is that molecules first appear in a certain order or structure, and then they get diffused step by step. And then there is the reverse process, the reverse diffusion, where we restore order from chaos. A diffusion model essentially gets trained to do just that, reverse diffusion, step by step, creating an image from chaos, from noise. Of course, creating is very different from destroying, and it's much more difficult than that. And that's what we're doing with Kandinsky. More specifically, how that happens. There is the forward process and the reverse process. The forward process is that we have an image, and then step by step we add noise to it. The formula is on the screen. We take a coefficient less than 1. We multiply the image by it, and then we add some noise. And then we add more noise, and if we select the right BTTs, then by adding noise gradually, more and more, in 100 or 1,000 steps, we end up with something that is very close to the normal Gaussian distribution. If you look at the formula, you will see alpha t. We want the beta t in a way that alpha t is close to 0, and then xt large. If alpha t is approximating 0, will then be close to normal, which is what we want. But beta t is also an important factor. A lot depends on it. This correlates with the noise that we're adding to the image. Why are we adding noise? Because at a later stage we are going to remove that noise. This removal of noise happens like this. If we knew that qxt minus 1 plus xt, that would be simple. We could sample some random noise, and then step by step we would be sampling it from known distributions. We would get our image. But we do not know the q. And if we do not know the q, what do? We take a manifold and maximize the similarity with our distribution. That's what we do. Of course, xt minus 1 could adhere to the condition of xt 0. This is normal distribution with the u and b parameters. We know them. And then we will be approximating this probability. We do not know this. pxt is normal. We are sampling from the normal distribution. And beta is once again normal distribution with unknown average, which is exactly what we need to approximate. We are building a neural network that will be approximating the average. But that is obvious. To some extent, we need to be able to take any xt step, and on the condition that we know the xt, we need to be able to take the noised image and denoise it. The method of maximizing the similarity logarithm, clearly this is a model with latent variables, so from the bottom we can build an evidence low bound. Evidence low bound is then maximized. It turns out that the loss is pretty standard, because this is the sum of divergences in all t times across the whole sampling between the beta and the q. The normal distribution is proportionate to the square of differences of averages. The loss is known, As muteta, we take the UNet, the classic architecture, and there you have it. You select the parameters of UNet to minimize the loss. That was the unconditional generation, but nothing is keeping us from adding conditions. Conditionality happens as this. We have text, some piece of text, we encode it with, I don't know, fly no 2, doesn't matter which one, and then we feed the textual embeddings into our UNet. The UNet gets trained the same way, meaning each time the UNet is trying to predict the next less noisy element in the sequence, and as a result, we end up with the final picture. Kandinsky 3.0 works the same way. This is the general operational scheme for all diffusion models. We had Kandinsky 2.2, and they had this specific thing. In addition to the green UNet, they also had one more block, which took the blue text embeddings and transformed them into visual clips, which helped to somewhat improve the quality of final generation. But it also produced some shortcomings, because instead of training one element in the big neural network, we had to train two. In the Kandinsky 3.0 version, we decided to step away from the diffusion image prior or image mapping and substitute it with experiments with the UNet architecture. We trained UNet way more, 5 times deeper compared to Kandinsky version 2, and then we took encoder fly no 2. In the column on the right, you see the comparative characteristics, the text of the encoder. You see it grew more than tenfold by the number of parameters, which, as we expected, would give a boost in text understanding. UNet grew, and it also gave us a boost in image understanding. Cheburashka, the Kandinsky 3.0 generated image. By the way, we had 1.1 billion data sets of texts, 256 by 256. We first added the biggest data set of images, and then we increased the sizes of the images. I wanted to show you several comparisons of Kandinsky 3.0 as compared with Midjourney and Kandinsky 2.0 and 2.2. With the different prompts, broadly formulated prompts, it is better than Midjourney in image quality generation. We did an honest side-by-side comparison, and we asked people what is better, Kandinsky 3.0 or the previous version, Kandinsky 2.2. The first question was about image understanding, 2 images and a prompt, and the people had to answer. And the second question was about which image is better visually, by visual quality. On the top is the domain-based text understanding. I don't know if you see the domains. On the bottom is the assessment of visual quality. The understanding of domains in Russian, yellow is Kandinsky 3.0, green is Kandinsky 2.2. The understanding of Russian domains significantly increased, and you can see that on the common graph, not by domains, but generalized. 53 versus 32. A few more prompts. I especially like the octopus wearing a hat and a tuxedo with the St. Basil's Cathedral in the background. Looks cool. We also augmented inpainting and outpainting painting features. We added these modifications to the main model so that the model could not just generate it based on text, but so that it could also process as input some initial part of a picture. So it is picture and text. We can generate the forest with the creek and then inpaint the Iron Man into it. Or we can generate Cheburashka on red square, and then we want this red square to be by the sea. So we can add that as outpainting. we are generating in the endless canvas mode. Where can you test drive Kandinsky 3.0? You can scan the QR code for the Telegram bot, or on the right, the website of fusionbrain.ai. On the website, you can also generate and inpaint. So this is a good tool for designers. The one with the bot, in that version, all the previous versions of the model are also available. A few words about video generation. Kandinsky learned to generate video. It can generate video in several ways. It can use images, so we generate an image and then we outpaint it based on new prompts, and then we reverse it. So this is not a video model, this is just Kandinsky outpainting. Then there is the animation mode. In addition to text, it accepts a certain mode of transformation, and the most interesting one, the end-to-end method, with a pack of frames which is perceived by a human as a video. There's also the Kandinsky animation method, the Diffusion method. What happens is we have the initial image generated based on text, and we want to slide to the right. We are moving this image to the right, and then we use the image-to-image properties of the main model, which essentially mean this. We can add some noise to the image, just a little bit to the bad image after the shift, and then we denoise it, and it will be a good picture. Kandinsky and any diffusion model is able to do this. And we can do the same thing many, many times, and then it will be a shift to the right. This is simply the properties of Kandinsky 3.0. How do you do this shift? You can do it as follows.
You can calculate the depth map based on the image. And then you can get the projection based on some transformation, like the transformation of a skew will be that. It will not be realistic, but after image it will become possible. This is how image-to-image animation works in Kandinsky. So Maxim has already showed something. I'm going to show you another video that is generated by the AI. I think it looks great, but the best thing was that we released was Kandinsky Video. Kandinsky Video is a full-fledged model for video generation. Now, what happens here? Basically, in the pipeline, we have two models. This is the model to generate the main frames. So we actually predict a set of images. Those who use image brain site, they will look at it and think that it is a video. So this model generates a pack of frames, and it is denoted, and that's how we have the video. Now, it is illustrated here. We take a diffusion, a model, modify them, and add some layers, and then we use UNet 3D to make it a video. Now, this pipeline is a very complicated task because the video in the worst case scenario is 24 frames per second. If it's 23, it will look like a slideshow. Now, the generation of the basic frames, it can be processed by one model that will give you 2 frames per second, and all the other frames can be delivered by the more lightweight interpolation model. It's the same, but it denoises the central frames. You denoise the central frames, and you deliver the first and the second frame. Basically, the modification from 2D to 3D is done by the temporal There's not a lot of data. If you learn the model from scratch due to lack of data, you won't be able to train it properly. If you look at only temporal layers, then the generation quality, image generation quality might go down. The training sets, these are the something that will lack, and we as a community must increase them in volume. We have created the Kandinsky video parameter. We have added our own temporal blocks, not even layers, and actually we published a research paper on that. And the model has this number of parameters. You have to multiply all of them. It is what we train is temporal blocks here, because we have some elements from the Kandinsky model. Now, there are some cons to that. They are not interpretable and they are not correlated with the metrics that humans have. Although, can I go back? Yeah. So based on these metrics, we are leading in text-to-video models, in all text-to-video models. In open source, we were #1, but Stable Video Diffusion was released yesterday. It is a little bit better quality-wise, but well, that's a race. And we will try to make sure that we win in this race. And these are some of the examples. This is the Kandinsky video generated by the Kandinsky. You can use this QR code, send us an application, and we usually approve all the applications quite quickly. Now, there are 3 things to consider here. Now, the models for generating videos are the videos used by ad designers. It can be used every day. And this is the image generators. As for the video generators, it is still in research phase. I think that in several days, the quality of the image generation will be translated to the quality to the video generation, and you should. Why? The images are 1024 by 1024 pixels. Do you use the training data sets with this resolution? Because if you look at the photos, there will be like 3:2 ratios, or they will have other ratios. This is a unified, most friendly format. Because this is the square, and it's very easy to measure the quality, to develop, to compare different models. But Kandinsky could generate another resolution. 9:16, 16:9, 2:3, 3:2. These are the resolutions also available on our website. Thank you very much. And as far as I understand,